Hey guys, how you doing? Happy Tuesday night. It's about 8 o'clock. Sorry I haven't got anything to you yet today. Been busy doing a lot of research, and I'm doing my own reverse engineering project right now. Everybody knows about the shortage of available masks that are in certain areas. So I've been working on a design or prototype that looks like this. It uses sectional pieces, and then this comes in and out. Plug it in, put a new piece in, snaps into place. My 3D printing project I'm working on right now, so let me just grab you here and we'll go over. Here you can see it printing. My home office. Trying to put this practical use of engineering and exactly what we're talking about. Reverse engineering something for quick production. I've been reading a lot about companies transferring their 3D printing over to making things like this. They're not FDA approved, but they're better than nothing. So without further ado, I'm going to give these to a first responder and have him tell me what he thinks about it, if it's something that he would like and if we should move forward with it. So without further ado, let's get into 6.3, which is reverse engineering and functional analysis. Alright, so what is reverse engineering and it's kind of scope? It's a process of taking something apart and what makes it tick? What makes it work? Haha, get it, tick, watch, yeah. What is the structure, the function, and the operation of each individual component? So we know that everything has pieces parts. Well, with those pieces parts, they all do something. Nothing is just there for fun. So why is reverse engineering used? It's used to document things. It's used for discovery of how something works. It's used in the investigation, and we use it for product improvement. If you've noticed, I believe Apple was the first to come out with AirPods, and then all of a sudden the other companies are also coming out with them. That would be, they've reverse engineered it. They took apart a set of AirPods, figured out how they worked, tried to put their own spin on it, and come out with their own product. Why we use it for documentation? If you're creating an instruction manual, you need to be able to document how something works or how something goes together. Also, if you ever want to fix it, you need to know how it works. So maintenance requires documentation. Discovery. This is both academic and just basic curiosity. How many of you when you were younger took something apart, usually tried to put it back together and ended up with extra pieces parts? Not the way reverse engineering is supposed to work. This is why this was your curiosity. That's why we take pictures of things. The beauty of having cell phones lets us take quick pictures of whatever we're working on so that we can make sure it goes back together in the same fashion that we took it apart. Also for military and commercial intelligence. Investigation. So we analyze and test things. Document patent infringement. That's a big one. That's the really expensive one. If you're caught with patent infringement, usually there's lawyers involved in big settlements. And for design failures, remember I talked about engineers who their job is to find out why something failed. This is one of the things they use reverse engineering for. What actually failed on it? Was it, and whose fault? And then we use it to improve or redesign a product. So increase efficiency of it, improve reliability, improve manufacturing, eliminate failure, reduce cost, increase ease of use, reduce negative environmental impacts, or what parts can we recycle? So part of your engineering, reverse engineering culminating lesson that you're going to do is you're going to reverse engineer something that maybe you think could be better. The rule of thumb for this project is 3 to 13 parts and non-electronic. So 3 to 13 parts, non-electronic, because you have to be able to take this thing apart, figure out how it works, make an improvement, and then put it back together, preferably with the improvement. For this one, we may not get to the improvement because of 3D printing. That's usually how we reverse engineer and make our modifications, we 3D print stuff. However, if, and I say if as in when, you design something using Inventor. Remember that download is free for students. You just need to use your student login to create an account. You're able to design something, send it to me as an STL, and I will 3D print it for you. So, tools of reverse engineering. Micrometers, I've showed them to you, but I haven't taught you how to read them. Calipers we've used. Optical probe, you can find that on the mill. Medical imaging, very expensive, we don't have that in class. And handheld 3D laser scanners. I've had students try to use these, kind of a generic one. We used to have one of the MakerBot ones. It didn't really work like it should have. So these aren't really as cracked up or as great as that we hope they are at this moment yet. But technology is advancing so fast that I look for them to be really spot on here in the very near future. So the stages of the reverse engineering process: visual analysis, which we've already done. Functional analysis, that's what we're working on right now. And structural analysis is also, that'll be our next component that we look at. So functional analysis, what is it? What is the purpose that is identified for the product? So what does it do? And then we determine how the product functions. And then what are the inputs and outputs that are listed? And you're going, wait a minute, I don't understand this. Well, that's okay. So let's look at something very simple that hopefully you're all familiar with. The toothbrush. It's been around for a minute or two. A lot of them are electric. Mine is. So the purpose of a toothbrush is to clean teeth and gums to prevent tooth and gum decay. Water and cleansing paste are used in conjunction with the brush. Cleansing paste is toothpaste, so we don't get any confusion there. So the function. So here's an annotated sketch of, it looks like probably one of those Crest spin brushes. All the components are listed, and we do a hypothesis of what is the function. So stores electricity. We assume that that's what this does. Toggles the electricity. We assume that's what that does. We know that this is a handle grip. We know that this houses something. We know that there's a conversion of electricity to torque here. Remember, torque is a rotational force. And then we have bristles, and this head rotates. So we don't know exactly what is like in here. We have to make a guess, but we give it a label. So we use what's called the black box system model. We identify what goes into it and what is the output. So what is our input? It does something, and then we get an output. So let's look at this a little further. This is where we represent internal components, which are unknown. So we don't actually know what that electrical conversion to torque is, and we don't know what components are housed in there. We also don't know what batteries used. We have to make assumptions, or we throw them in the black box and give our inputs and our outputs. So inputs, we have a hand motion. We use toothpaste. We use water, and there's energy. That electrical energy is converted to mechanical energy. What are the outputs? Remember, we lose everything to sound and heat first. Also, we have a waste product, the toothpaste, whenever you spit it out. Another output is clean teeth and gums. So that is what a functional analysis looks like. So let's go in now to simple machines to sort of help you understand some of the simple machines that you're going to see within your actual product. There are 6. So the first one is a wheel and axle, pulley, lever, incline plane, wedge, and a screw. So you're going, okay, how does that apply right now? Well, there's work that's done. Work is a transfer of energy from one system to another. So we have electrical converted to torque, and then we can figure out how much work is being done by the amount of force and the displacement. So work indicates a force is exerted on moving something. This is where I would do my book demonstration. If I'm holding the book in midair, is work being done? Yes or no? Hopefully you said no, because there's no displacement. Now if I'm picking the book up off the ground, yes, work is being done because the book is moving. So keep that in mind whenever you're looking at these things. So wheel and axle, everybody thinks of a car. Not this wheel and axle. Everybody thinks of this wheel and axle. This is one example where the axle is driving the wheel. On a car, here's the other example where the wheel is now driving the axle. So you have to take into account when you're looking at a wheel and axle is what is doing the driving. Is it the wheel or is it the axle? And then we have special wheels and axles called gears. Usually a wheel with teeth. Teeth of one gear push against the teeth of another gear. This is how we get things to move. Some of you might not know what this is unless you're like me and grew up with a grandpa who loved to make waffles and pancakes. That's a hand blender. This is what a watch looks like at a very microscopic level. And here's another example of a finer watch. A pulley is another example of a wheel and axle. All it is a wheel with a rope running over it. Pulleys change the direction of the force, and if we put multiple pulleys in series, we reduce the effort required to move an object. If you notice, this one requires 10 pounds of force to move an 80-pound object, where a fixed pulley is 10 pounds of force to move a 10-pound object. And then we have a lever. As a kid, this was probably your favorite device in the whole world, the teeter-totter. How many of you were the bully and never let the other person down? Just kidding, but seriously. And then this is an example of Newton's theory. He said, give me a lever long enough, I can move the world. So there are 3 types of levers, and each lever has these 3 forces. So we have an effort force, a fulcrum, and a resistance force. And it's real easy to understand which class of lever is it if you can remember free, F-R-E. So for a first class lever, the fulcrum rests between the effort and resistance. There's the F. So the F is in the middle of a first class lever. Effort and resistance are in the same direction. Second class lever. This is our R. Notice what's in the middle. The resistance is in the middle. So we have our fulcrum over here. We have our effort over here opposing our resistance. This would be a wheelbarrow. And finally, our third class lever, which is the E in the F-R-E, which is the effort in the middle. This would be an example of something you don't want to build because it's not very mechanically efficient. And then we have an inclined plane. All it is a slanted surface to raise an object to its determined level. Wheelchair ramps, loading ramps, on-ramps. And then we have specialized inclined planes, just like we have specialized wheels and axles. A wedge. This is a moving inclined plane, and a screw is basically an inclined plane wrapped around a cylindrical shaft. Don't let that one fool you. So then what is a wedge? It's an inclined plane that moves. Triangle shape with a sharp point, used to split, cut, tighten, or hold things together. And then a screw, like I said, inclined plane wrapped around a shaft, used to fasten things together or to move things. In PoE, a couple of them used an incline or a screw to move marbles. They've used a worm gear to move, an apparatus. So guys, that's all I have for today. The PowerPoint ran about 15 minutes, so your assignment will be shortly following this, and it's a functional analysis. So what do I mean by functional analysis? Alright, let me pull this over here to my screen. So, an example of a functional analysis. And remember, everything we're doing here is the alternate because we're not using the Automoblocks vehicles. So the purpose or primary function of the object. So what does it do? So this is an example of stapler, what model it is. Its device is to mechanically bind sheets of paper together using a metal wire. They went through and they identified the different parts. Remember, 3 to 13 moving parts. If you pick something like, a yo-yo, that would be 2 parts if you don't take it all the way apart. Then you make an educated guess of how the product operates. So we assume this is how it works. There isn't much that we can't see as far as this goes. So our input, staples, loose paper, and an applied force. The function is to fasten paper. Outputs, noise, heat, and bent staple. What mechanical components are visible? So base plate, riser, pivot pin, magazine, anvil, staple, lever arm. And then what are the functions? So I want you to take this product that you've used hopefully from the beginning, and I want you to keep working with the same product. So you should have one product, again 3 to 13 parts, not electronic because that throws a curve. And I want you to work with that whole thing through this entire reverse engineering project. So what this project is you're going to improve this in the end to make it better in some way, shape, or form. Okay? So that's all I have for tonight. Have a great night. and I'm looking forward to conversing with you guys in the future.